This podcast is brought to you by HEC Paris.
I'm going to talk about dimension invariant dynamic storm structures. This is joint work with Adlai Fischer, who spoke this morning, and Liren Wu from Baruch College. So if you look at the term structure interest rates, I think we realize that it's hit by shocks that have many different degrees of persistence, right? So at high frequency, we know that large transactions impact a particular maturity and tend to dissipate through hedging or statistical arbitrage. If you look at medium frequencies, we know that monetary policy shocks tend to be implemented through short rates and then dissipate through the yield curve. And then at low frequencies, we know that inflation and innovation also have and real GDP growth tend to have some interesting implications on the yield curve. Okay? So we have these shocks. The shocks have different degrees of persistence, and they affect different segments of the yield curve in different ways. Now, so that suggests that we should, when we model the yield curve, we should probably incorporate these frequencies. And in theory, nothing prevents us from doing so, right? So we know that n-factor models are well developed and analytically tractable. And in particular, we know that in the affine class, we can have as many factors as we wish. Okay? So there's no limitation coming from theory. However, in practice, we know that the models that are most commonly estimated tend to be low-dimensional, okay? And predominantly have 3 factors. It's rare to use more than 3 factors, okay? And the argument is that 3-factor models capture major variations in the level, the slope, and the curvature of the yield curve. Okay? However, these models suffer from significant empirical limitations. Okay? We know, for instance, that they imply counterfactually large cross-correlations between maturities, as noted by Dye and Singleton. We know that the forecasting performance is poor. Generally worse than the random walk, as noted by Greg Duffy. And perhaps even more importantly for practitioners, the residuals of these models, right? So when you want to fit a model, you end up with residuals that are economically significant relative to the beta spread, which implies that 3-factor models cannot be used very easily. Okay? Okay, so that's the situation. We have 3-factor models. They do an okay job, but perhaps we can do slightly better. But of course, if you want to have more factors, then we need to face the curse of dimensionality. Okay? We know that the number of parameters of a generic affine model tends to increase quadratically with the number of factors. So a generic 3-factor model already has over 20 parameters, okay? And many of these parameters cannot be effectively identified. Yes, already working with 3-factor models is hard. Okay? So in this sense, the models provide too little. They cannot match critical features of the data, and too much in the sense that they have too many parameters to be effectively identified. Okay? What can we do? Well, what this suggests is that there could be gains by specializing within the affine class. In other words, what we're trying to do in this paper is find some structure in the data that has not yet been exploited. Okay? More specifically, what we do is we propose a high-dimensional factor structure that effectively captures shocks of many frequencies. Okay? This is going to be done by considering heterogeneous shocks to the short rate. We're going to see that these shocks are going to be identical in size, except for differences in persistence. The persistence of the components is going to be very parsimonious. We're going to assume that it's going to be specified by geometric progression. Which, by the way, is an idea that Adlai and I have explored in our earlier work on multi-frequency volatility modeling. But in fact, as you'll see, the technology is quite different. Okay, so it's the same inspiration, the same spirit, but the technology itself is going to be very different. Okay, so what are the properties of these models? Well, even though we have an arbitrary number of factors, we'll see that 5 parameters are enough to control the time series and the term structure, regardless of the number of factors. In practice, we're going to work with 15 factors. Okay? We're going to see that the term structure is matched to near perfection, so the errors are less than 1 basis point. That is less than the order of the beta spread. We'll see that the parameters are estimated with high statistical significance. We match well the sample cross-correlations and autocorrelations of bond yields. And we have some interesting applications. We'll see that this model is well suited for yield curve stripping. We'll also see that out of sample, we do better than traditional benchmarks. Okay? Okay, so this is what the model delivers. So let me give you an outline of the talk. First, I explain how we capture the dynamics of the short rate. Then we'll see how we can price bonds. Talk about estimation, and then I'll provide some applications. Okay? All right, so let's start with the short rates cascade. We're going to model it under P, under the physical measure. We define the statistical dynamics of the short rate RT in the following way. So we're going to have a cascade of Orstiel-Uhlenbeck diffusions. Okay? So level 0 of the cascade is just theta r. It's just a constant. This is a long-run level of the short rate. Okay? Now, set j is equal to 1 here. Right? The first factor is mean reverting around theta r at speed kappa 1. Okay? And then you add a shock, right? A Brownian shock. And then factor j, more generally, mean reverts around factor j minus 1, okay, at its own speed kappa j. Right? And then, of course, there's going to be a shock that's specific to factor j. Okay? So it's really a cascade of mean reverting processes. Each process mean reverts around the previous process in the cascade. Okay? All right. And we assume that the short rate is the last factor in this construction. Okay? So it's the idea that it's driven by shocks that have very different degrees of persistence. And so these factors have, as we're going to see, are going to have delayed effect on the short rate. Okay. All right. So we in the paper, we consider a fairly general specification with arbitrary kappa j's, arbitrary sigma j's, and so forth. But in the presentation, I'm going to focus on a Bayes model in which the decay rates follow a geometric progression. Okay? Kappa j is kappa 1b to the j minus 1. So 2 parameters are going to be enough to specify all the kappa j's, of course. And then we're going to assume that the volatility is constant across frequencies. Okay? So let me give you some intuition for this specification. So if you look at the bond market, right? If you think about the maturities that are the most liquid on the bond market, right? What do we see? Well, we have 1 month, we have 3 months, we have 6 months, so etc. So what happens is each maturity is kind of, twice or 3 times the previous maturity. Right? You go from 1 to 3, you multiply by 3. From 3 to 6, you multiply by 2. So roughly speaking, there's a geometric progression, right, in the most liquid maturities. Okay? Now, there must be a reason to that, right? Liquidity is endogenous. So we know that on the one hand, it's good to have a number of markets that are liquid, right? Because it can provide information and so on. On the other hand, having a liquid market is costly, right? So somehow there must be an equilibrium there. We don't model it specifically, but the fact that the most liquid maturities are approximately geometric, roughly speaking, in the market means that, this is an appealing specification. Okay? Now, the maturities are not exactly geometric. So what we're doing is not tautological, right? But we're inspired by what we see in the market to specify the decay rates. Okay? And now, since the markets are endogenous, since the information that they're providing is endogenous, it's not completely absurd to assume that the information content of each market is approximately the same. Hence, the idea that the sigma j's, are approximately equal. Right? This is just a pragmatic specification, but at least you can see where we're coming from. Okay? All right, so in total, what we have is a cascade that's fully specified by 4 parameters, right? Kappa 1 and b, which specifies the frequencies of our model. Sigma 1, the size of the shocks. Theta r, the long-run level of the short rate. Okay? And you can have you can have 2 factors, you can have 15 factors, the number of parameters remain the same. Okay? Now, what's the role of the factors, right? How can we think of the factors, right? So we see that the short rate is equal to the highest frequency factor, right? The lowest, you can think of it as being high in the cascade, low in the cascade. So we see that we're down here, right? So what is the effect of the other factors? Well, it has to be a delayed effect. In order to make this concrete, what we do is, we denote by x naught the state of the economy, and what we do is we represent RT as a function of the initial state and stochastic integrals over the shock. So we have a different representation. Okay? What you see here is that, if xj naughts are the initial factors, you see how the expected value of the short rate t periods ahead. Okay? And then, of course, these are response functions. So, the value of RT also depends on the realization of all the shocks between 0 and t. But in expectation, you can see how the response function AJT that are going to tell us how a particular factor affects the short rate t periods ahead. Okay? Now, what we do is that what we show is very straightforward, is that the response functions AJ tau are convolutions of exponentials. Okay? So in particular, they are available analytically. Okay? All right. Let's look at these response functions, because they really tell us how a factor has a delayed effect on the short rate and how this delayed response would look like. So if you look at factor n, ANT is the exponential of minus kappa n nt. So it's decreasing, right? So we know that initially, the short rate is equal to to factor n, right? So n of 0 is equal to 1, correspondingly. And then the effect of the highest frequency factor is going to decay, right? And the rate of decay is controlled by kappa n. Okay? What about factor n minus 1, right? Well, it's a convolution product of two exponentials. So, you can very easy to show that it satisfies this expression. When tau is equal to 0, an minus 1 is 0, corresponding to the fact that factor n minus 1 has no instantaneous effect, right, on the short rate. Okay? As tau increases, this becomes positive. It increases. So as tau gets larger, the response function goes up, reaches a peak, and then declines to 0. Okay? So there is a maximum response time. Okay? More generally, what we show is that the lower frequency shocks tend to generate ham-shaped response function with maxima occurring at progressively longer horizons. Okay? All right, so this kind of tells us how factors influence the short rate, and here we illustrate the response functions. This is the effect of the response function of factor n. Goes down quickly, right? It's the most transitory factor. And then you can see that this is the effect of the response function of factor n minus 1, the response function of factor n minus 2, and so forth, right? So the first factor, which is represented here, has a very delayed action, right, on the short rate. Okay? Now, because we assume that the kappas follow geometric progression, we can show in the paper that in log scale, this response function are translated versions of each other. Okay? All right. So this was an example, well, whatever, there's some numbers. Okay, so we understand how to specify the short rate under the physical measure. Now we want to think about bond prices. Okay? So we're going to have to change measures. So let me introduce some notation. So we denote by P of T and cap T the price at date T of a zero coupon bond paying off $1 at date cap T. Standard notation. In the absence of arbitrage, we know that there exists a risk-adjusted measure such that bond prices can be written this way. How do we go from the risk-adjusted measure to the physical measure? Well, we just, multiply the discount rate by this product. Gamma JS is the price of risk, the market price of risk, and we assume that it's affine in XT. Okay? So in the paper, we solve. We show that we can solve for bond prices in the affine case, right? And when we have affine risk premia, okay? What I'm going to do in this talk is I'm going to assume that the gamma JTs are equal to a constant, right, for all J's, and there is going to be no lambda J effect. Okay, just for simplicity today. All right. That's our base model. Gamma jt is equal to gamma 1. Okay? You can write the factor dynamics under Q. This is what it looks like. Now, you see that the rate of mean reversion is the same under the statistical measure and under the risk-adjusted measure. Okay? What you see also is that the risk-neutral mean of the lowest frequency component, I mean, you just think about if j is equal to 1 here, right? You're going to have kappa 1 times theta r minus gamma 1. Okay? So these are constant terms, which imply that under the risk-adjusted measure, the long-run level of the short rate is not theta r, but is theta r minus gamma 1 times the volatility of the shocks divided by the speed of mean reversion of the first component. Okay? And that's true for factor 1, but you can derive the same results, similar results, when you're looking at factor j's. So the effect of the market prices of risk is to distort the long-run level, right, of each of the factors. Okay? Now, if gamma 1 is negative, then you see that theta rq, the long-run level of the short rate under Q, is greater than the one under P. Okay? So typically, you're going to be around, we're living in the physical measure. So typically, we're going to be around theta r. Right? But so the short rate is going to be around theta r. But we're going to anticipate when we're under the risk-adjusted measure, we're anticipating to go to a higher level. Right? So the obvious implication is we're going to have an upward sloping yield curve, right, if gamma 1 is negative. Okay? So we're going to get that through the risk factors. Okay, one thing I want to emphasize is that there's a 1-to-1 relation between theta rq and gamma 1. Okay? And it's easier for us to think about theta rq than it is to think about gamma 1. So in the estimation, what we'll do is we're going to estimate theta rq. Okay? And if we're interested, we can back out gamma 1. We will not be interested in that today. All right, so this is how we price bonds. Now we know, it's an affine model. It's exponential affine. So the price of a bond maturing in tau periods when the state of when the factors are given by xt can be written in this way. The coefficients b of tau and c of tau solve a system of ODEs. And what's nice is that these ODEs have analytical solutions. So if you want to program this for trading purposes, it's all there, right? You can just program it. So you're going to get the answers very fast. Okay? Now, in this case, in the case we're looking at b of tau, right, which controls the, if you want the zero yield, is the integral of A of S. Right? In other words, you said that the zero yield is the average level of the short rate, so not surprisingly, you get this particular result. Okay? That's going to be a handy result. And then the intercept has an interpretation that's provided in the paper. Once we have this, we can compute the forward rates, of course. And because B is the integral of A, when you take the derivative, you get back to A. Okay? So when we assume constant risk premia, there's a very tight connection, very high correlation, a perfect correlation, in fact, between the forward rate and the short rate, right? But that link will disappear as you introduce richer risk premia, right? And this is what we do in the paper. Okay. Now, what happens when the number of factors becomes large, right? What is the behavior of this construction, this particular cascade? Well, so to be specific, take a fixed set of parameters, gamma 1b, sigma 1, and theta r. What we show is when the number of factors n goes to infinity, the sequence of short rate processes converges in L2 to a limit process that has continuous sample path and a finite variance. Okay? So that's the result under P. And then when you don't mess things too much through the risk premia, you also get convergence of the entire term structure as n goes to infinity. Okay? So we have nice convergence. So even though we have an infinity of factors, we have a convergence to a well-specified process, which is informative for the empirical work in the sense that we don't expect our prices to get wild as we add more and more factors. Okay, so it's a nice stability property. All right, so it's time to look at some empirical results. Here we're focusing on 6 LIBOR and 9 swap rates. It's the US data weekly between 1997 and 2007. You can see these are the liquid maturities we're looking at. As you can see, when you go from one to the next, one value to the next, you have a ratio of 1.52. It depends on the particular case, but you can see there's this kind of approximate geometric progression that I was alluding to before. Okay, it's coarse, but that's the point. The model is not tautological, right? Okay, let's estimate this model. So, well, we can cast it as a state space model. XT is a hidden state. LIBOR and swap rates can be viewed as observation with errors. We use because the measurement equation is nonlinear in XT, we can use the uncentered Kalman filter to infer the states from the observation at each date. We can then compute the log likelihood function and estimate kappa 1, B, sigma 1 theta. So this is what specifies the dynamics on the Q. Theta RQ, because now we add also the risk premium. That's supposed to be the same for all factors. And then you have an observation noise sigma. So you have 6 parameters. Right? 15 factors, 6 parameters. And that's easy to estimate, no problem. And these are the results. Okay. All right, so what you see, so each row corresponds to a specification. This is a specification with 1 factor, 2 factors, 3 factors. We're going to use the 3-factor specification as a benchmark as we move further, as we go through this talk. And then finally, we look at the 15-factor specification. Okay? So what you observe is that this is in yearly. So kappa 1 is about 20 years, right? So the lowest frequency has a duration of 30 years. You can see that theta R goes down to 0, and this is something we're not particularly happy with, but we don't fully understand. The long-run level of the short rate is 0. This is what we estimate. Sigma 1 goes up slightly as we increase the number of components. Theta RQ, as you can see, is larger than theta R, right? So we get on average an upward sloping yield curve. Okay? B goes down, so the frequencies become more tight, get closer to each other as you increase the number of factors. Sigma A goes down dramatically. Okay, so you get less and less error, right, as you have more components. But basically, this is less than 1 basis point. So be careful. This is square, and then it's in percentage points. So when you adjust it, it becomes of the order of a basis point, if not less. And then this is the likelihood function. It goes up very fast. These models are non-nested. You can compare them by computing some wrong test, and you think that the difference is, that the 15-factor model does better than all the lower dimensional specification, and that the improvement is significant. Okay. So these are the main results. Well, we have well-identified parameters. I forgot. Well, in the paper, we actually report the standard errors. Here for space constraint, I didn't do it, but all the parameters are well specified, well identified. The lowest frequency is about 20 years, the highest a couple of days. The average term structure is upward sloping. Pricing errors are negligible, and we prefer higher dimensional specifications. Okay? We also test the scaling restriction. What happens when the kappa j's are freely estimated? So that's a much bigger estimation. So we get something which is approximately scaling. It's not overwhelming, but it's not there's something there that seemed to be valid. That's an interesting comparison. We look at the cross correlation of weekly changes, right? So we use as a benchmark 6-month LIBOR, and what we do is we compute the cross correlation between the weekly changes inside the 6-month LIBOR and the weekly changes of, say, a 30-year zero coupon bond. Okay? And what do you get? What you get is that with a 3-factor model, you really miss out. You don't really capture well the cross correlation of weekly changes, but with the 15-factor model, the fit is quite good. Okay? So we've kind of fixed the cross correlation problem that Singleton and Dye were pointing out in their 2002 paper. Okay? Let me show you some applications. Well, this model is really well suited for stripping, right? If you want to extract the forward rates, this is something which is often used in industry. You assume that the rates are piecewise constant, and you tend to get this type of forward rates. If instead you use our model, which means you fit the yield curve at a given point in time, extract the factors, and use the filtered factors to figure out the forward rates by using the formulas I was giving you before, this is what you get. You get nice, smooth, arbitrage-free forward rates. Okay, and here you see how this forward curve varies with time. Okay. What else do we get? Well, we look at out-of-sample performance, right? So we use as a benchmark. So we have more results in the paper, but what I'm going to show you here is you look at the AR1, a simple AR1 process, right? You assume that the yield on a particular maturity follows an AR1 process, and you use that to forecast, the yield of a given maturity. Okay. Now we know that the random walk is actually a pretty hard benchmark to beat in this literature. Okay. So what we report here is a relative error that is 1 minus the mean squared error of the model forecast divided by the mean squared error of the forecast coming out of the random walk model. So the random walk model has a big advantage, right? What does it say? It says our best forecast of the yield curve is the current yield curve. Okay? At least we start at the right starting point. Right? There's no fitting problem when you use the random walk. Okay? So this gives the random walk a big advantage over a number of models, okay, including 3-factor models. Right? So that's one reason why the random walk is a good performer out of sample. Now, what we see here is we do our model does better, right, than the random walk, and the difference is statistically significant. This is all out of sample, right? So there's no look-ahead bias. Okay. So we do better than the random walk at maturities of for maturities of say 1 month to a year, and at horizons of 1 week to 4 weeks. Okay. So in the short run, our model, if you want to make short-run forecasts, and those of you who are traders or, trade at relatively high frequency, this is what you need, right? You need to be able to forecast interest rates, in the relatively short run. And this is a tool that allows you to do it. Okay. If you instead use an AR1, the problem with the AR1 is it's a less parsimonious approach, and the results tend to be worse. So this is, let me just summarize the out-of-sample forecast, because we think that's one of the nice features of our model. AR1 is not parsimonious. One AR1 on each series, right? So for each maturity, you fit an AR1. This requires 30. Well, 50, there's a problem with the multiplication here. So 15 times 2, or 30 parameters already. Okay. And if you were fitting a general var, of course, it would be much more. You would even have even more parameters, more instability problems, and so forth. Okay. So we like to think that the cascade model is simple. It's as simple as possible, but not simpler, right? So it's as simple as possible in the sense that it's flexible. It uses a small number of parameters. It's sufficiently rich to fit the yield curve perfectly at a given point, and thereby give you a good forecast. Okay. So in conclusion, I would say that the idea of the paper is to take a general affine model, make some key assumptions. We consider a cascade factor structure, which means that we eliminate factor rotation. And also as a result, we pin down the meaning of each factor. And this is achieved by a natural separation of the frequency components. We achieve a tight specification by assuming that 2 parameters control all frequencies, because we assume that the kappa j's, remember, are geometric. And we also make some simplifying assumptions on volatilities and risk premia, namely that these are the same for all factors. Okay? And what do we get as a result? We get what we call the dimension invariant dynamic term structure model, where the number of parameters does not depend on the number of factors. This class of models has a well-behaved limit. There's no curse of dimensionality, so we can estimate these models fairly easily, and the estimates are stable and well identified and statistically significant. And what's nice is that empirically they work well, right? So we get improvements over lower dimensional specifications over a number of fronts. So you can use these models to strip the yield curve. You can use them to forecast the yield curve over horizons of, say, 1 to 4 weeks. Thank you.
Please visit us at www.agc.edu.